Assalamualaikum and very good day to everyone. Today we'll be presenting our project entitled Design and Simulation of RF Microwave Filter using Insertion Loss Method in ADS. This project was carried out under the supervision of Dr. Zaki and Dr. Wan Hazrila as part of the BET 3414 RF Technique and Microwave Course Requirement. In this presentation, we will explain the objective, design methodology, simulation process, and the performance analysis of the low pass and band pass filter design using ADS software. This is our group member of this project. Our group consists of Muhammad Syami Afiq, Muhammad Farhan, Muhammad Azhad, and Muhammad Irfan. Each member contribute to the filter design, calculation, ADS simulation, result analysis, and slide preparation. The first objective of this project is to design low pass and band pass RF microwave filter. The second objective is to apply the insertion loss method in the filter design process. Next, we simulate the filter circuit using ADS software. Finally, we analyze the filter performance based on frequency response and insertion loss. And from this analysis, we can determine whether the filter meets the required specification or not. For the introduction, microwave filter are important components in RF and communication system. They are used to control signal transmission based on frequency. The main function of the filter is to allow the desired signal to pass and attenuate unweighted signal, noise, and interference. Microwave filters are widely used in modern communication system such as 4G, 5G, satellite communication, wireless communication, and radar system. In this project, the filters are designed using the insertion loss method and their performance are analyzed using ADS software. Next, basic filter theory. A microwave filter allows selected frequency signal to pass and block unweighted frequency signal. For a low pass filter, signal below the cut-off frequency are allowed to pass, while higher frequency are rejected. For a band pass filter, only signal within a selected frequency range are allowed to pass. There are two types of filter implementation in this project, which are lump element and distribute element. Lump filter use inductor and capacitor, while distribute filter use transmission line or microstrip line. Another important parameter is insertion loss. Insertion loss show how much signal power is lost when the signal pass through the filter. And a good filter should have low insertion loss in the pass band and high attenuation in the stop band. Next, I will pass to Azhad.
Okay, thank you to Muhammad Farhan. Next is my part, calculation low pass filter. Okay, this is my cut-off frequency is 3.1 gigahertz. My insertion loss is 47 dB at 6.2 gigahertz. Ripple 3 dB. Assume RO 50 ohms. The formula is W over WC minus 1 equal 2 pi F over 2 pi FC minus 1 equal F over FC. When we insert the value 6.2 GHz over 3.1 GHz minus 1 equal to 1. From the graph, we got N equal to 5. Okay, next, for G1, G2, G3, G4, G5, and G6, I get the value from element value for 3 dB ripple. For G1, the value is 3.4817, G2 0.7618, for G3 4.5381, for G4 0.7618, for G5 3.4817, and the last one G6 equal 1.0000. For the first calculation, I find the C1 for capacitor, and the formula is G1 over RO 2 pi FC equal, and when insert the value, G1 is 3.841 over 50 multiply 2 pi multiply 3.1 gigahertz, and the answer is 3.94 picofarads. Next, I will find the inductor value L2. The formula for L2, RO multiply G2 over 2 pi FC equal, when we insert the value, RO is a 50 multiply G2 0.7618 over 2 pi multiply 3.1 gigahertz, and the answer is 1.955 nanohenry. Okay, next, we continue from the previous slide. For C3, also same, we use the formula G3 over RO multiply 2 pi FC. When we insert the value, G3 is 4.531 over 50 multiply 2 pi multiply 3.1 gigahertz, and the answer is 4.66 picofarad. Next, for L4 equal RO multiply G4 over 2 pi FC, and when we put the value is, RO is 50 multiply 0.7618 over 2 pi multiply 3.1 gigahertz, and the answer is 1.955 nanohenry. And the last one for C5 equal G5 over RO multiply 2 pi FC. When we insert the value for G5 is 3.4817 over 50 multiply 2 pi and multiply 3.1 gigahertz, and the answer is 3.57 picofarad. Okay, next, this is Richard transformation. Okay, as we can see, uh, our n is 5. When n is odd, so we should start with capacitor. It's mean open circuit, short circuit, open circuit, short circuit, and the last one is open circuit. Okay, for the formula for open circuit, 1 over G1 equal 1 over 3.4817, and the answer is 0.287 for the open circuit. And the short circuit is maintained, G2 equal 0.7618, and open circuit again, we use the same formula, 1 over G3 equal 1 over 4.5381, and we get the value 0.220. And G4 for open circuit, for the short circuit is 0.7618, and the last one for the open circuit, the formula is same, 1 over G5 equal 1 over 3.4817, and the value we get is 0.287. Okay, we continue from the previous slide. Okay, next, next part, uh, we should change the left and right open circuit to the short circuit, and we use the formula, and I can explain in my next slide. Okay, we continue from the previous slide. Okay, this is the formula for the left and right side open circuit, and we want to change to the short circuit. Okay, for the first one is Z1 equal to 1, Z2 equal 0.287, N2 equal 1 plus Z2 over Z1 equal 1 plus, and when we insert the value 0.287 over 1, and the answer is 1.287. Okay, next, Z1 over N2 equal 1 over 1.287, and we get the answer is 0.777. And then Z2 over N2 equal 0.287 over 1.287 equals 0.223, and we change to the right side. Z1 equal 1, Z2 equal 0.287, N2 equal 1 plus Z2 over Z1 equal 1 plus 0.287 over 1 equal, the answer is 1.287. Next, Z1 equal N2 equal 1 over 1.287 equal 0.777. Next, Z2 over N2 equal 0.287 over 1.287, and the answer is 0.223. Okay, if we can see, this is when the open circuit we change to the short circuit, and the value we put at the short circuit 0.223, and we put at the 0.777, and the right side we put the value 0.77 and 0.223, and then we draw again the diagram, and we separate to the four part A, B, C and D, and we maintain the open circuit at the middle, and we put the N2 for the every part. Okay, next, when we separate for the each part, we should calculate every part of we separate. Okay, the first one is A. Z1 equals 0.023, Z2 equal 1, N2 equal 1 plus Z2 over Z1 equal 1 plus, and when we put the value 1 over 0.223, and the answer is 5.484. Next is N2 Z1 equal 5.484 multiply 0.223, the answer 1.223. Next, N2 Z2, the formula, and when we put the value 5.484 multiply 1 equal 5.484. Next, we calculate for the B part. We use the same formula. Z1 equals 0.7618, Z2 equals 0.777, N2 equal 1 plus Z2 over Z1 equal 1, and when we put the value 0.777 equal 0.777 over 0.7618 equal 2.019. Next, N2 multiply Z1 for the formula, and when we input the value 2.019 multiply 0.7618 equal 1.538, and the next formula, and N2 Z2 equal 2.019 multiply 0.777 equal 1.568. Okay, for the next part is C part. It's a same formula we use. Z1 equal 0.7618, Z2 0.777, N2 equal 1 plus Z2 over Z1 equal 1 plus, and when we put the value 0.777 over 0.7618, and the answer is 2.019. Next, N2Z1 is the formula, equal 2.019 multiply 0.7618, and the answer is 1.53x. Next, N2Z2, the formula, when we when we put the value, change the value, 2.019 multiply 0.777, the answer is 1.568. Okay, the last one is the part D. Z1 equals 0.023, Z2 equal 1, and 2 equal 1 plus Z2 over Z1 equal 1 plus 1 over 0.223 equal 5.484. Next, N2 Z1 equal 5.484 multiply 0.223 equal 1.223. And the last one, N2Z2 is the formula. When we put the value, 5.484 multiply 1, and the answer is 5.484. Okay, next, when we settle all the calculation before this, we put all the value inside of the um, every part in the diagram I show. For the starting, we put number 1. So the lower, we put 5.484, 1.223, 1.568, 1.538, 0.220, 1.538, 1.568, 1.223, 5.8484, and the last one is 1. This is for the normalized value. Okay, next, this is the denormalized value with a 50 impedance for different stub. For we multiply all the value with the 50 ohm, so we get a new value is a 50 ohm, 274.2 ohm, 61.15 ohm, 78.4 ohm, 76.9 ohm, 11 ohm, 76.9 ohm, 78.4 ohm, 61.15 ohm, 274.2 ohm, and the last one is a 50 ohm. Okay, this is the last part. For the last part, we draw the the diagram, and just we put the value before this into this diagram. So 50 ohm, 61.15 ohm, 76.9 ohm, 61.15 ohm, and the 50 ohm. 274.2 ohm, 78.4 ohm, 11 ohm, 78.4 ohm, 274.2 ohm. Okay, that's all for my part. Thank, thank you. And I will pass to Shahmi.
Hello, my name is Muhammad Shami Afiq, and my next slide will be the bandpass filter design. We designed a bandpass filter with a center frequency of 3.1 gigahertz and a bandwidth around 350 megahertz. Using this specification, we calculate the lower and upper cutoff frequencies, which are approximately around 2.925 gigahertz and 3.275 gigahertz. We also determine the fractional bandwidth value required of the design, the design. So after obtain the design parameter, we develop the bandpass filter schematic in ADS software. The circuit consists of both series and a parallel LC resonators arranged according to the insertion loft method. The normalized prototype value to G1 to G5 always calculate the component values. The next one is to show the calculation for the shunt or the parallel resonator sections. Using the fractional bandwidth characteristic, impedance, and center frequency, we calculate the inductance and capacitance value required for the parallel bunches of the filter. Now we are calculate the series resonator components. The inductors and capacitor were derived from the prototype value and design equation. These components form the main signal path and help define the passband characteristics. And these are the lumped bandpass implementation. So the complete of this bandpass filter was implemented and simulated in ADS. The design combined the calculated series and parallel resonators to achieve the required center frequency of 3.1 gigahertz and a bandwidth of 350 megahertz. The simulation result confirmed that the filter meets the intended bandpass response and demonstrates the effectiveness of the insertion loss method in radio frequency microwave design.
Okay, thank you, Azhar. Next, we go to low pass lamp design. This slide show the low pass lamp filter design in ADS. The lamp filter is designed using inductor and capacitor. For this design, the cutoff frequency is 3.1 gigahertz. The ripple is 3 dB, and the source impedance is 50 ohm. The filter order obtained from the insertion loss graph is n equal is 5. The final component values are used in the circuit are capacitor and inductor such as C1, C2, C3, L1 and L2. This design is the basic theoretical design before converting to distribute transmission line form. Next, low pass lamp result. This slide show the simulation result for the low pass lamp filter. From the graph, we can observe the S21 response of the filter. At the cutoff frequency of 3.1 gigahertz, the value of S21 is approximately negative 4.109 dB. At 6.2 gigahertz, the attenuation is approximately negative 52.050 dB. Since the required insertion loss is 47 dB at 6.2 gigahertz, this result show that the low pass lamp filter successfully meet the stop band requirement. This means the filter can pass lower frequency signal and attenuate higher frequency signal effectively. Okay, next, distribute low pass design. This slide show the distribute low pass filter design. The distribute filter is designed by converting the lump element filter into transmission line form. Richard transformation is used to convert inductor and capacitor into transmission line stub. Then, Kuroda arithmetics are used to make the circuit more practical for microstripe implementation. This type of filter is more suitable for microwave frequency because transmission line perform better than lump component at high frequency. This slide show the simulation result for the distribute low pass filter. The result show the frequency response after the circuit is simulated in ADS. At 3.1 gigahertz, the S21 value is approximately negative 3.110 dB. At 6.2 gigahertz, the attenuation is approximately negative 116.317 dB. This show that the distribute low pass filter has strong attenuation at the stop band frequency. The result also show that tuning is important because it helps the filter performance match the required specification more accurately. Next, distribute low pass layout. This slide show the layout of the distribute low pass filter. The layout represent the physical microstrip design of the filter. In this design, open stub and transmission line are used to replace the lump components. The layout is important because it shows how the circuit can be implemented practically on a substrate or PCB. Overall, this distribute low pass filter is more suitable for microwave application because it reduces parasitic effect and provide better high frequency performance. Next, I will pass to Shami.
Next part, discussion. All RF filter were successfully designed and verified using ADS simulation, where the results show that the lump low pass filter achieved the required 3.1 GHz cutoff frequency as expected from the theoretical design. The distribute low pass filter was successfully implemented using Richard transformation and Kuroda entities, and it performed improved significantly after tuning and optimization in ADS. The lump bandpass filter also meet the required specification with a 3.1 GHz center frequency and 350 MHz bandwidth. However, small divergence between theoretical and simulation result occur due to substrate loss, parasitic effect, and impedance mismatch. Conclusion. In conclusion, the insertion loss method has been proven effective for designing RF microwave filter. All design filter including lump low pass, distribute low pass, and lump band pass successfully meet their required specification through ADS simulation. The result also show the tuning and optimization are important to achieve accurate performance. For future improvement, the design can be future validated using EM simulation and hardware implementation. That's all for our team presentation. Thank you.